if I asked you to predict the products of the decomposition of ammonia, I would hope that you would write something like this. Additionally, if I ask you to write a synthesis reaction for the combination of nitrogen gas with hydrogen gas, I would hope that you would write something like this. So as you can see, when you have ammonia, nitrogen, and hydrogen, both a decomposition reaction and a synthesis reaction are possible. The reaction that actually occurs depends on which reactants you have. In chemistry, it is assumed that all reactions can proceed in both the forward and reverse directions, just like in this example. Chemical equilibrium is reached when you have a reaction occurring in a closed system and both directions take place at equal rates. This means that if you had a closed container with ammonia, hydrogen, and nitrogen in it, you would eventually have both the decomposition reaction and the synthesis reaction occurring at equal rates. The closed container part ensures that as one reaction proceeds to completion, the buildup of product doesn't go anywhere and can eventually react in the reverse direction. Instead of writing both equations like this, though, double arrows can be used to signify a reversible reaction. Of course, as we said earlier, all chemical reactions are technically reversible. However, this doesn't necessarily imply that every time we write a reaction, we should always write a double arrow. Sometimes we write a single arrow because we are only discussing one direction. Sometimes we write a single arrow because, while the reverse process is theoretically possible, it's not really that practical. Also, sometimes one direction occurs more than its reverse direction, making a system product-favored or reactant-favored. Remember, the most important condition for saying a system is at equilibrium is to say that that the two processes are happening at equal rates. But this doesn't necessarily mean you have equal amounts of everything involved. For example, imagine a Tupperware full of water. If you set that water in the sun all day, eventually the processes of evaporation and condensation would reach equilibrium. They would reach equal rates. However, that doesn't mean that the amount of water and the amount of water vapor are equal. That part kind of depends on the temperature. It simply means that the rates are the same. Once equilibrium is established, imagine that for every one molecule of water that evaporates, you get another molecule of water vapor that condenses. So, while you have the two processes happening, and it's considered dynamic because things are changing, the actual overall volumes of the water and the water vapor are not changing. Another way of looking at this is to consider a reaction coordinate diagram like from the last chapter. If you look at this, you will see that in one direction it is exothermic, but in the other direction it's endothermic. We discussed this concept during our thermodynamics chapters. You can also see that both directions have very different activation energy barriers. Thus, while both reactions are possible, one is more difficult to initiate and would require a higher temperature to occur. To more quantitatively discuss the position of equilibrium, meaning if it's established, if it's reactant favored or product favored, we can compare the relative concentrations of the products to the concentrations of the reactants in a ratio. So for example, if you have a reaction such as this, A plus B goes to C plus D with the respective coefficients, the ratio comparing the concentrations would be like this. But because those coefficients of the balanced chemical reaction can be used in stoichiometry as well as in kinetics to compare the relative rates of appearance and disappearance, you must also incorporate them into this expression as well to get something that looks like this. So the product of the concentrations of the products raised to their coefficient divided by the product of the concentrations of the reactants raised to their coefficients can be divided to equal a value called the equilibrium constant, which is the K. So if we have a reaction such as this one, H2 plus I2 goes to 2HI, the equilibrium constant expression would be the product raised to the second power because of its coefficient, divided by the two reactants raised to their coefficients. All right, some important rules about calculating the equilibrium constant are as follows. First of all concentrations must be equilibrium values, which means they must be values that are measured after the system reaches equilibrium. If you envision a graph of a reaction comparing these concentrations, you would have something like this. At the start of the reaction, you have primarily reactants. But as the reaction proceeds, the concentration decreases and then slowly plateaus. The products, on the other hand, start at 0, but as the reaction proceeds, their concentration increases until they plateau. In this way, you can see that there's this point at which both lines have plateaued, and this is where equilibrium exists. All right, the second thing that you need to know about the equilibrium constant is that the product concentrations always, always, always appear in the numerator, and the reactant concentrations always appear in the denominator. The value of K depends on a particular reaction, and it also depends on a particular temperature. Additionally, there are never units given with K. Solids are never included in equilibrium constant expressions. And the molar concentration of water is never included in equilibrium constant expressions because in aqueous solutions, water is both a part of the products and the reactants, and there's so much of it that its relative concentration doesn't really change. If you're working with a reaction involving gaseous reactants and products, it is also possible to calculate an equilibrium expression, or constant, in terms of the partial pressures of each of the gases, since the partial pressures directly relate to the amount of each gas present at equilibrium. In this case, the expression is written in a similar way, but utilizes pressure values instead of concentration values. It solves for something called a Kp instead of a Kc. All the values we've talked about so far can really be abbreviated as Kc, and what we're going to be talking about now is the same expression, but it's a Kp. In order to convert between a Kc and a Kp, consider the ideal gas law. In this case, pressure equals the moles over the volume. And technically, moles over volume is the very definition of concentration. So you can look at it as the pressure equaling the concentration divided by R times T. The relationship between the respective K values is related in this exact same way. If you look at this equation, it's pretty similar. The Kp is going to equal the K of the concentration times R and T raised to this delta N. The delta N is the number of moles of product minus the number of moles of reactant. And you can get those from the balanced chemical equation. It's just looking at the coefficients. So, in an example, if you have a given value of Kp, such as 5.8 times 10 to the 5th, and at that standard temperature, you can calculate its Kc for the reaction using that conversion equation. It's going to look like this. You'll input it into the equation, and up here, in place of the delta N, we're going to have the 2 from here, and the 4 comes from adding the 3 and the 1 from the reactant side over here. Essentially, that's going to give you a Kc value of 3.5 times 10 to the 8th. Let's look at this K value a little bit more. If you look at the way the ratio is determined, it's the products over the reactants. This means that if you have relatively equal concentrations of both, the value of K will be close to 1. If you have more products than reactants, the value will be a big number. And if you have more reactants than products at equilibrium, the value will be a small number. It might even be a fraction. So if you look at the chart on page 731 in your book, and I'm going to transition out of the PowerPoint to do that. So here's the chart on page 731. And this lists a few possible equilibrium constant values. If you look at these, you'll see the ones on the top are relatively big. We've got 4.2 times 10 to the 52nd. And as we move down here, actually I should kind of take this away. Ends right here. And if we look down at the smaller numbers, starting with 1.7 times 10 to the minus 3, we'll see that those numbers are significantly smaller. and they're listed as reactant favored. Okay. So the large numbers are because you have a lot of product, because it's a product favored reaction, and the small numbers are so small because you have a reactant favored reaction. Equilibrium values, as you can see, change depending on which of the two reactions is more dominant. All right, let's go back to the PowerPoint. As you can see, I have listed up here an equilibrium constant expression that's pretty similar, except instead of equaling K, I have it equaling a Q. Sometimes we don't know if a reaction has made it to equilibrium yet or not. What we do know is perhaps a K value because we have it from a textbook. Okay. But we don't know if the reaction that we're currently working with has made it to equilibrium or is just approaching it. For these reactions, we can calculate something called the reaction quotient, which is this Q value. It looks exactly like calculating an equilibrium constant, but these values are not necessarily at equilibrium. What we can do is we can put in whatever concentrations we have and calculate a ratio value, and we can then compare it to K. And if we compare it to K and determine that it's the same number, that tells us that we are actually at equilibrium. So let's do a quick example. If we look over here, if we've got a K of 5.5 and a Q of 1.3, this tells us that K is significantly greater than Q, which means that in order for these numbers to be the same, in order for us to reach equilibrium, Q needs to get bigger. Okay? The only way to get Q to increase is by increasing the top of this ratio. The only way to increase the top of that ratio is to move towards the product side of the reaction. So this reaction needs to tend towards the product side, the forward direction, in order to reach equilibrium. Okay. To summarize this, if Q is less than K, some reactants must be converted to products for the reaction to reach equilibrium. This will decrease the reactant concentrations and increase the product concentrations. If Q is greater than K, what we need to do is some products must be converted to reactants for the reaction to reach equilibrium. This will increase the reactant concentration and decrease the product concentrations. But you can always look at that equilibrium constant expression and determine if it needs to get bigger or smaller to tell you whether the reaction needs to proceed in the forward direction or the reverse direction. All right, now take a minute and complete a problem. Complete exercise 16.3 and actually 16.4 on page 734.